Today we're diving into something you've probably seen visually, maybe as a poster. The Mandelbrot set.
Ah, yes, instantly recognizable.
But believe us, there's just a whole universe of ideas packed into this one mathematical thing. It's way more than just a pretty picture.
Oh, absolutely. The sources we looked at really drive home it's profound significance. It's foundational, really, touching so many parts of mathematics.
Right. So our mission for this deep dive is to figure out why. Why does this seemingly simple rule? I mean, it fits on one line, generates something so important and, frankly, captivating.
It's a great question.
We're going to look at its role in fractal geometry, complex dynamics, even chaos theory. But, try to keep it understandable, avoid drowning you in jargon.
Sounds good. Where should we start? Fractal geometry.
Yeah, let's start there. Its role in popularizing fractals.
Okay. Well, the Mandelbrot set was genuinely pivotal there. Before it came along, fractals were, well, they were a bit niche, you could say.
A mathematical curiosity.
Sort of, but the Mandelbrot set was just so visually compelling, so rich. It really grabbed the imagination, not just of mathematicians, but, the public too.
And it all boils down to this incredibly simple equation. Zn plus 1 equals Zn along plus C.
That's the one, where Z and C are complex numbers, and you always kick things off with ZO being 0.
Seems straightforward enough. But repeat that simple step over and over.
And boom, you get this object of, well, seemingly infinite complexity. It's a perfect example of how simple, iterative rules can generate enormous intricacy. That idea pops up everywhere.
So the core concept is about whether the sequence stays bounded.
Right.
Exactly.
The Mandelbrot set is basically the collection, the set, of all those complex numbers C, where the sequence of Z values you get doesn't just fly off to infinity.
It stays put, sort of, within a certain boundary.
It stays contained, yes. If it stays bounded, C is in the set. If it escapes to infinity, C is out. And that simple decision, made for every single point C, defines this incredibly detailed shape.
And the boundaries where things get really wild, yeah, when you zoom in.
Absolutely. That's where you start seeing these smaller versions of the main shape popping up. They're a bit distorted, not perfect copies.
The mini-Mandelbrots or satellites?
Precisely. That approximate self-similarity is key. It's not the perfect repetition you see in some simpler fractals, but it's there, and it really flew in the face of traditional, smooth Euclidean geometry.
Right. Traditional geometry gives us nice, neat dimensions. A line is 1D, a square is 2D.
But the boundary of the Mandelbrot set, its edge, its dimension isn't an integer. It's actually got a Hausdorff dimension of 2.
Dimension 2. But isn't that the dimension of a flat plane? How can a line-like boundary have dimension 2?
Well, think about it like this. It's so incredibly wiggly, so infinitely detailed, that as you zoom in, it effectively starts to fill up space like a 2D area would. It's infinitely long in a finite space.
Wow.
Measuring it is like trying to measure a coastline perfectly. The closer you look, the longer it gets. That non-integer dimension is sort of the heart of fractal geometry.
Okay, so it's a key fractal.
Yeah.
But it's also called a map of complex dynamical systems.
Yeah.
What's that about?
Right, so think bigger picture. That equation, FCZ equals Z safs plus C, that's actually a whole family of functions.
Because C can be any complex number.
Exactly. Each different value of C gives you a slightly different function, a different rule for iterating Z, essentially a different dynamical system.
Okay.
And the Mandelbrot set acts like an index or a map for this entire family. It tells you something fundamental about the behavior associated with each C.
I've heard about Julia's sets being connected to this. How do they fit in?
Ah, yes, a really elegant connection there. For any given C, there's a corresponding Julia set. Now, if that C is inside the Mandelbrot set,
Then
the associated Julia set is connected. It's all one piece, however complicated it might look.
And if C is outside the Mandelbrot set?
Then the Julia set shatters. It becomes this disconnected cloud of points, what mathematicians call a Cantor set, or fat dust.
So the Mandelbrot set is like a lookup table. Inside means connected Julia set, outside means fragmented.
That's a great way to put it. It organizes the infinitely varied world of Julia sets.
And the boundary again. You mentioned it's a bifurcation locus. Sounds important.
It is. It means that as you move the parameter C across that boundary line, the behavior of the iteration changes dramatically, qualitatively.
How so?
Well, for example, stable cycles where the Z's values eventually fall into a repeating loop might suddenly appear or disappear as you cross the boundary.
So fundamental shifts in the system's long-term behavior happen right at the edge of the Mandelbrot set.
Exactly. It's the place where stability tips over into a different kind of dynamic. The boundary encodes these critical transitions.
It really is like a directory then. The Mandelbrot set itself showing the main structure, and its boundary detailing all the points where the associated Julius sets undergo these fundamental changes.
Precisely described.
Okay, so we've got its role in fractals, its role as this map of dynamics. Now let's connect it to chaos theory.
Yes, another crucial link. The Mandelbrot set is, in many ways, a visual icon for chaos theory.
Chaos theory, the butterfly effect and all that. How does this picture relate?
Well, think back to the Julius sets. For certain values of C, often points near the boundary of the Mandelbrot set, the corresponding Julius set exhibits extreme sensitivity to initial conditions.
Ah, so if you start with slightly different Z's values.
Their long-term behavior under iteration can diverge wildly. One might stay bounded, another might fly off. That's the butterfly effect, right there in the dynamics governed by C.
Even though the rule itself is simple and deterministic. Fascinating. What about the edge of chaos?
That's often how the boundary is described. You can sort of think of the interior of the set as representing relative order points stay bounded. Orbits might be periodic or stable.
Okay.
The exterior represents, well, a faster escape to infinity, maybe more straightforwardly chaotic in that sense.
And the boundary.
That's the frontier. Infinitely complex, mixing properties of both regions, it's this place of exquisite tension between order and unpredictability, the edge of chaos.
Visual boundary between stable and unstable regimes. And you mentioned something about universality, how chaos emerges.
Yes. This is really cool. There's a very common way complex systems transition into chaos called the period doubling route.
Seen in things like population models, right? The logistic map.
Exactly that. And incredibly, that whole scenario, that sequence of bifurcations where stable cycles double in length again and again until chaos sets in, it's encoded visually within the Mandelbrot set, mainly along the main axis, going into the big cardioid shape and the bulbs attached to it. As you move towards the boundary along that real axis, you see structures corresponding precisely to those period doubling bifurcations.
And the rate at which they happen that connects to those Feigenbaum constants we'll talk about.
Precisely. These universal numbers that describe this route to chaos in many systems, they are fundamentally linked to the geometry of the Mandelbrot set. It's quite profound.
It really is. Okay, so exploring this wasn't just math theory, right? It needed computers. Big time.
Oh, absolutely. Exploring and visualizing the Mandelbrot set went hand in hand with advances in computing power and techniques.
You couldn't just calculate a few points.
Not if you wanted to see the detail. You needed to iterate that equation millions, billions of times for countless points C just to render one image.
Which must have pushed things forward.
Definitely. It drove the development of faster fractal generating algorithms, clever ways to map iteration counts to colors to actually see the structure.
Coloring is key to visualizing it, isn't it? Otherwise, it's just black and white.
It is. The color schemes help reveal how quickly points escape, highlighting that amazing boundary structure. And sometimes, to zoom really deep, you even need special high-precision arithmetic because standard computer numbers aren't accurate enough.
So the desire to see this thing actually spurred computational innovation.
Without a doubt. And importantly, those images weren't just for scientists.
Right, they captured the public imagination.
Totally. Suddenly, this abstract mathematical concept was producing these stunning, almost psychedelic images. It made math seem, well, beautiful, accessible, exciting to a much wider audience. It was a fantastic gateway.
Yeah, which brings us nicely to that idea of mathematical beauty, blurring lines between art and science.
It really did. You look at these intricate, organic-looking patterns, and it's hard not to feel a sense of awe. It showed that math wasn't just dry formulas. It could generate things of genuine aesthetic power.
Made it less intimidating, maybe.
I think so. It sparked curiosity. How could something so complex come from Z star plus C?
And does that have philosophical angles, too? The simplicity generating complexity idea.
Oh, for sure. It makes you think about order versus chaos. How intricate structures can emerge from simple rules. You see echoes of that in physics, biology, everywhere. It kind of forces you to ponder the nature of mathematical reality itself.
It's pretty mind-boggling stuff. Okay, so we've covered fractals, dynamics, chaos, computation, beauty. But the sources also mentioned universality and connections to other fields.
Yeah, this is where it gets really interesting, showing how deep these ideas run. We touched on the Feigenbaum constants.
The rate of period doubling.
Right. The fact that these specific numbers, derived from the Mandelbrot set structure, also describe the onset of chaos in completely different systems. Fluid dynamics, electronic circuits, population biology is just staggering. It points to universal laws governing chaotic behavior.
So the Mandelbrot set isn't just an isolated curiosity. It taps into something fundamental about how complex systems work.
That's the idea. And it's not just those constants. Mathematicians have found other Mandelbrot-like sets, parameter spaces for different iterated functions that share similar structural properties, these intricate boundaries separating different dynamic regimes.
Suggesting these kinds of maps are a common feature in mathematics.
It seems that way, yes. It hints at deep unifying principles governing iteration and complexity.
What about connections to the physical world, like modeling nature?
Well, that's a bit more indirect and sometimes debated. You don't find perfect Mandelbrot sets sitting out in nature, obviously.
Yeah.
But the ideas from fractal geometry, heavily inspired and popularized by the Mandelbrot, set ideas of self-similarity, non-integer dimensions, complexity from simple rules, have definitely given us powerful new tools.
Tools for what?
For modeling things that traditional geometry struggles with. Think coastlines, mountains, clouds, turbulence in fluids, the branching of trees or blood vessels, things that look sort of similar at different scales.
So fractals provide a better language for describing that kind of natural complexity.
In many cases, yes. The Mandelbrot set helps show that such complexity could arise from simple mathematical processes, making it seem less mysterious, perhaps, that nature produces such forms.
It gives us a way to think about generating that complexity. Okay, and despite all this knowledge, all these connections, it's still being researched actively.
Oh, absolutely. It's kind of amazing. Decades later, there are still major open questions.
Like what?
One of the biggest is the MLC, the density of hyperbolic components conjecture.
Okay, what does that mean, roughly?
Roughly, it asks if the nice parts of the Mandelbrot set, the bulbs, the regions corresponding to stable periodic behavior, are densely packed together. Do they fill up the whole interior, or are there other kinds of structures lurking in between?
And we don't know the answer.
We don't. Proving it would tell us a lot about the fundamental texture of the set. It shows that even its basic layout isn't fully understood mathematically. And researchers are still digging into the precise mathematical properties of the boundary, its exact size, in a measure-theoretic sense, its detailed structure. Plus, people are exploring variations, like 3D Mandelbrot sets, or sets based on different kinds of functions. The exploration is far from over.
Incredible that something so visually familiar can still hold such deep mathematical mysteries.
It really highlights the depth hidden in that simple formula, Z1 plus C.
Okay, so let's try to wrap this up to bring our deep dive to a close for today. The Mandelbrot set. It's clearly not just some random pretty picture.
Definitely not.
It's a cornerstone of fractal geometry. It helped launch the field. It's this amazing map of complex dynamics telling us about Julia sets.
It's a visual guide to chaos theory, showing sensitivity and that edge of chaos.
Yeah, and it drove computer science forward, pushed visualization. It's a source of real mathematical beauty, bridging art and science.
And it connects to these universal principles like the Feigenbaum constants appearing in all sorts of different systems.
And amazingly, it's still a hotbed of mathematical research today.
Absolutely. That simple equation, iterated over and over, just holds this unbelievable richness that continues to teach us things about math, complexity, and maybe even the world around us.
So a final thought for you, our listener. Think
Yeah.
about other simple rules or patterns you see, maybe in nature, maybe in technology. Could they, like the Mandelbrot set, be hiding unexpected depths, whole universes of complexity and beauty? What other deep dives might reveal something similar?
A fascinating question to ponder.
Thanks for joining us for this deep dive.